Thank you, Leonardo. And thanks for the opportunity to give a talk here in Edinburgh again. I did my undergraduate master's here, so it's always nice to come back. There's quite a few people in the audience that have some ties to Edinburgh. Yeah, so as said, I'm going to talk about my recent work on scattering amplitudes that are relevant for Kerr black hole scattering. So, okay, I mean, maybe I really don't need to do the motivation for this crowd, but the idea is that we can extract some classical information from scattering amplitudes, maybe by computing scattering observables, which can then be related to maybe some observables for binary black hole like orbits and even mergers. And that's particularly interesting now, given that we have all these detections of gravitational waves, which are majority generated by binary black hole systems. Now, the in-spiral phase can be treated perturbatively, which is great if you want to use scattering techniques. And in particular, well, there's many different perturbation schemes you can do. I guess just to name a few, there's the maybe more traditional post-Newtonian approach, which involves weak gravity and also slow relative velocities. So you don't need to treat everything. You don't need to consider like the full relativistic physics. And I guess just on this diagram here, which might be out of date, I guess this is the state of the art here for the corrections to the Newton's potential. Or you can study a different type of perturbation scheme. So it's weak gravity, but fully relativistic. And this one's more appropriate for the scattering regime. And I guess the benefit of doing Minkowskian is that you, at each order in G, you're able to get, I guess, all orders in the velocity. Great. So I have this little cartoon at the top, which is discussing this, I guess, pipeline of how you go from scattering amplitudes to, I guess, classical observables. And there's, I guess, like three main steps. The first is to start with your tree level amplitudes. And like, I guess you have to know which ones to choose, study them, construct them. And once you have your amplitudes in hand, you can sew them together depending on which observable you want to construct using different techniques. And then, okay, there's some non-trivial step here, maybe matching to a Hamiltonian or just at the level of the observable, doing some analytic continuation. And just really to discuss some of the current status, there's like really high PM results already at the scalar case. So if you just have a non-spinning black hole, so up to 4 PM, and there's definitely some progress already in 5 PM. But as soon as you want to model a spinning black hole, we are not able to go as high in PM, or, well, okay, maybe that's wrong. We can go pretty high in PM, and there's people in the audience who have, but it's to some fixed order in spin. Or, okay, at lower orders in the perturbation, there are some all spin results, but I guess there's a complication once you allow your bodies to have spin. You have to, I guess, either you can encode like all the possible like freedom that your body has to like interact and how that spin is encoded. So for example, you can model neutron stars in this way, or maybe you want to ask, okay, how does a Kerr black hole interact? In which case it should be pretty special. It's restricted. There's no freedom anymore. And it's still unclear actually what even at 2 PM that would look like. And the majority of the reason for that is that it's still unclear what this amplitude here would be if you want to consider a Kerr black hole. And that's the like main area of my research. Yeah, really focusing in on what is the correct ingredient, what is the correct scattering amplitude that encodes the physics of Kerr black hole. So at 3 point, we have a candidate, and it was written in 2017, a while ago. It was written completely unrelated to this, so Kerr black holes. It was just some nice 3-point amplitudes written in spin helicity. This is like a general spin amplitude, right? So this is a quantum number S here. So if you pick it, S equals 1 is the scattering of 2 massive spin 1 particles with a graviton. This is the graviton polarization, or at least like square root of it. And great. And why does this encode any physics? Well, actually, if you write it in some new variables, you find that it's like exactly the linearized energy momentum tensor for a Kerr black hole. You just need to write this in some special coordinates. So somehow there's this family of 3-point amplitudes in a QFT, which encode exactly the same information as the energy momentum tensor linearized energy. Okay, so unfortunately, when these were written down, they weren't written down as a Lagrangian. They were, and they're like 4-point analogs. If you construct them, like say with BCFW or other recursion techniques, develop spurious poles, essentially start incur problems at, I guess, as soon as you go at the interactions of spins above the force carrier. So in this case, the graviton. So what my work has been on is really trying to understand the origin of these 3-point amplitudes better. So what kind of theories are generating them? And once we understand that, can we construct some consistent 3-point amplitudes with what we've gained whilst studying the 3-point amplitudes? Great. So, right, and I guess the punchline of the first letter, I guess, published more than a year ago now, was that we found a set of higher spin constraints that uniquely predicted these 3-point amplitudes and corresponding 3-point amplitudes in like a corresponding gauge theory, which I won't talk too much about today. Great. So I'll just talk briefly about the approach that we took, and we'll talk about each step, I guess, in this talk. So the first approach is to construct the this effective field theory for Kerr. So this is this L. And the main point here is that we want to construct a consistent QFT of interacting higher spin particles. And that means you have to be really careful that you always have the correct degrees of freedom that once you have the interacting theory. And we did this, there's 2 approaches that we focus on, which I'll talk about after. Okay, and once you have this, you can construct and compute some quantum Compton amplitudes. So these are just, full quantum Compton amplitudes, and we'll see that there's some nice structure here, and we'll use that structure essentially to constrain the leftover freedom that we still have. I'll now say more about it later. And once you have the quantum Compton amplitudes, you can extract the classical physics. And I'll discuss a little bit about how people do that at 3 points. And I just realized I'm missing something here. In particular, there's an example in a paper with Paolo that we studied how to just extract classical physics from another set of amplitudes, just take some amplitudes of interacting higher spins from string theory, so the leading wedge states, and you can still extract classical physics from them. You just have to be careful about how to do it, and using that knowledge from studying it at 3 point, we're able to generate some order and spin classical amplitudes for a black hole. And indeed, this Compton amplitude matches the scenario scattering plane waves of a Kerr black hole background, which can be done just in GR using black hole perturbation theory.
Lucile?
Yes.
What is ROT?
Yes, sorry, I'm just realizing that there was a mistake here. What I wanted here was an amplitude. Maybe I can draw it.
Sorry.
No, it's good. I just realized now that I made a mistake. So what I wanted to write was leading wedges. So there's 3 point amplitudes for string theory. So take the leading wedge states, and they have some. So this is basically just saying you can have some massive spinning particle here with spin S, and some massive spinning particle here with the same spin, and the graviton, which is like the first state essentially in this leading wedge trajectory. And when you take the classical limit, you get the energy momentum tensor, linearized energy momentum tensor for a rotating rigid rod. So that's what rod was. And these are the polarization vectors of the graviton. So it's just to say that the classical limit is not, it's not just for Kerr. I mean, we've also had this morning, right? The classical limit is just some process which you have to define, or some procedure you have to define to extract classical information from quantum amplitudes. And when we look at this in particular, we find, I mean, that you have to be pretty careful once there's some spin involved. At least the way we do it, that you need to have some information about how an infinite spin particle scatters. But I have a slide on that later, so hopefully it'll be a bit clearer. Yeah, sorry about that. Good. So first I'll talk about constructing the high spin theories, and there's the two main approaches we use. So the first is perhaps the most standard approach. You take a tower of totally symmetric tensor fields. And okay, if you have like S+1 totally symmetric tensor fields, you have too many degrees of freedom. And then you have this nonlinear gauge symmetry, which relates them all, which helps you essentially cut down on your degrees of freedom so that you're landing on exactly the correct degrees of freedom for a spin S particle. So what's important is that even though you have a tower of many fields, it's all describing one physical state, the spin S state. Great. But once you add interactions, so that means minimally coupling your theory, you're going to break the gauge symmetry, and you need to reinstate it so that your degrees of freedom are, I guess, preserved. And that means that you have to add non-minimal interactions. And what we were able to find is that by constraining them using ward identities, which are essentially just related to corrections to this nonlinear gauge symmetry, so these ward identities, power counting, and also some soft high energy behavior constraint, which we call the current constraint, we were able to essentially uniquely generate these 3-point amplitudes that were related to Kerr. So somehow Kerr is like a particularly well-behaved higher spin theory, which has this softer high energy behavior. It satisfies all these ward identities and has nice power counting. For example, lower power counting than the leading register states in string theory. Great. There's a different formulation that you can use, and that's using a single chiral field. So it's no longer, so these are no longer Lorentz indices, right? These are spinorial indices, but the benefit is that you just need to use one. You don't need the tower anymore. And okay, you need to add if you want an interacting theory, you're gonna minimally couple it. But now you add non-minimal terms because you want to have parity invariant theory, which you don't get for free out of the box because you chose to encode everything in terms of a chiral field. And okay, what's the benefit of this? It's actually very compact. And now on the next slide, I'll show that we're able to write the cubic Lagrangian very compactly for it. This is like a general spin particle, right? Interacting particle. So yeah, so let's just say the results. So from the highest spin, like the tensor field construction, we found that we were uniquely able to predict these 3-point amplitudes. We found that when you go to 4 points, after fixing 3-point data and also imposing ward identities at 4 points, we find a reduced set of contact terms in this, this is in the gauge theory. So at 4 points for spin 2. And then as you go high in spin, okay, the numbers grow, but it's still reduced compared to the full freedom that you could have. Yes.
How different is this approach with respect to Behrens-Gille recursion relation?
So do you mean for the construction of the 4-point amplitude? How to well, I mean, it's in the same way that, well, isn't Behrens-Gille is you're solving the equations of motion like recursively, right? Is that correct?
You start with the three. Let's say that you have 3-point.
Mm-hmm.
Right? Mm-hmm. Then you start adding gluons in all possible ways. Right? Then at certain point you have to remove the redundancy in the amplitude. And perhaps this redundancy can be also removed once you apply more identities.
Okay, I'm not sure. Okay, honestly, I don't know. I think, yeah, the only thing I'll say is that once you have the Lagrangian, or okay, maybe it's more correct to say we have the currents, we don't build the full Lagrangian, you really just construct Feynman diagrams and then construct your amplitude out of Feynman diagrams. So I guess it's as different as usual. Like if you're going to construct an amplitude either by Berns-Giller or using Feynman rules, that's the same relation, I would say. But yeah.
So do you get like from this gauge symmetry like a formula for the number of contact terms that you will get to any order in spin, or
So
is
I would say no for computational reasons. So when you're using the totally symmetric tensor fields, it means you have this tower which grows at each spin each time you increase spin. So it becomes like computationally expensive because you need to ansatz each interaction between all the fields, right? Not just like the spin S field in the Lagrangian. So realistically, that means that in the gauge theory, the first non-trivial example is spin 2, because spin 1 has a massless theory equivalent. So it's special. So it's spin 2 and spin 3, which is not enough data points to, I guess, spot a pattern. And then gravity, spin 3 was already, this is the first non-trivial, I guess, spin, and it is flat. So I would say the answer is no to that.
Why do you consider integer spins?
Oh, also just sake of reducing complexity, because I mean, as soon as you add fermions to the picture, it can be done, and people who have done it in high spin literature. It's just, I guess, we knew we wanted to prioritize going to high spin, and ultimately, I guess if you want to go to infinite spin, it shouldn't really matter if you're going for the half integers as well or not. So just to reduce complexity. But it's true, it has been like, because it gets harder as you go higher spin, we did think, okay, maybe we should actually start doing the half integer spins in between.
But that's in the covariance, right? Does it make a difference in the chiral formulation?
Oh yeah, so yeah, maybe I can speak about it. So yeah, so it's hard in the parent picture, but when you have chiral, it's actually really easy to, well, it's much easier to treat things generically in spin. So this is the cubic Lagrangian for a generic spin S particle, which includes half integer spin. And right, like the spin 1/2 is the fermion, right? Like, so it's pretty fine to deal with. But I have to say that this approach, like just adding this term, this non-nominal term here, is the term that's needed to reinstate parity at cubic order. But it's not enough. It doesn't mean that your theory is now parity invariant at any order, right? Parity you need to impose at each order, right? And here, okay, we've covariantized, but in order for it to be parity invariant, you still need to add these operators L4. And I mean, parity is actually not super restrictive on that.
If there's a short answer to this, what is R minus?
Sorry, yes, there is. I can also write it out. It's the, I guess it's the curvature contracted with Pauli matrices. So now,
Oh, is it just the anti-self dual?
yes,
Okay, fine.
yes. And there's a reason for that. Like we chose a chiral field,
Yeah.
so there's only one type of index that can contract it. So you have to contract it with, I guess, Pauli matrices or van der Waals matrices that have always mean that you have the right type of indices. So yeah. And it's also because I guess you can consider this Lagrangian is correct if you consider all, let's say, all plus helicity. So if you consider one, like the interaction of two massive particles with n all plus graviton, so like they all have a plus helicity, then well, this thing doesn't contribute. Well, no, it won't contribute, I don't think. So this is enough. And it will generate like all these expected, these amplitudes that are known. And this was not done by us. This was already written for the free theory or that Okharov and Skvortsov wrote. I should have put citation. But yeah, so the problem is as soon as you have it, even just one minus helicity graviton, then it needs to be corrected for. Great. So given that, we can write out our Compton amplitude. And I've written it maybe in what looks like an overcomplicated way, but this is an amplitude, which is it just means any spin s like mass of particle interacting with a mass of particle of the same spin and two gravitons of the chosen helicity, then this is the Compton amplitude. And where does this generic spin dependence appear? It appears in these polynomials here, which I'll define on this slide. But it's just to note that like these pre-factors, it's just the polar dependence and the helicity dependence of the graviton. Okay, and then maybe like, but the generic, like the things that is just telling you whether you're scattering spin 1 or spin 2 particles is all encoded in these polynomials. And this amplitude matches the known Compton amplitudes that didn't have any problems at up to spin 2. It matches a previous spin 5½ result by these authors here. And yeah, as I said, you can encode all the spin dependence in these polynomials. These polynomials are polynomials in terms of spin variables, and these specific combinations here. I've just realized I'm missing a sign here. Sorry, there's some bugs. But they're particularly nice polynomials. They look like they're rational, like they might have poles, but this is just like a feature of what happens when you resum them. But in practice, they're just polynomials, which are called complete homogeneous symmetric polynomials. So it means take your variables, the number of variables is dictated by n, and construct all monomials that have degree k, and they all have coefficients 1. So this is P2 pretty simply here. So these seem to be really nice basis. It's a structure showing up in our amplitude. And what we will do now is we'll say, okay, we know we have freedom in the contact terms because we had this freedom in the quartic operators. Now we're going to impose that those contact terms are going to be constructed out of these polynomials. So that's an assumption, a choice. Yeah.
Can you go back to the previous slide? So if I remember correctly, for the spin 5½ when there was this paper of the shift symmetry, a couple of papers of shift symmetry, the answer that the case and chlorate law, they said that it couldn't match the spin 5½
Classically, right?
Right. So
but again, it's still, if you take the classical we should be able to land into the answers that they had. So how is it that this one that you have here agrees with this one and they didn't find agreement at that time?
right. So
Symmetric answer was into this 5½.
right. So yeah, I think there's two things to say, and one of them Andreas mentioned. The approach we take is we do a quantum amplitude, which is a function of the quantum number s, and then we're going to take a classical limit on it, and that limit actually dictates a little bit how to treat the quantum number. Whereas if we compare Case's work, and I guess Raphael, I'm not sure if you did, and their approach is more, okay, let's start. They start with a QFT amplitude, which is fine, and then they do the same thing. They take the classical limit, and then they add freedom, but they only add freedom in terms of classical contact terms, right? Whereas we will always add our contact terms as quantum contact terms and take the classical limit. And what does that mean? It means that things that come into play in the quantum amplitudes, right? So this is a quantum amplitude, it's matching. This can wash out in the classical limit, right? Maybe this thing that which the value of the term that was mismatching between the quantum amplitude, spin 5½ amplitude, and the classical amplitude they had, 5 minutes left, oh gosh, washes out in the classical limit. But maybe actually this is good because it's exactly here. I'm going to really skip this slide quickly. Basically, in order to do the classical limit with spin, you want to extract a spin-dependent quantity, which is a vectorial, I guess. We want to extract the ring radius of the Kerr black hole. And the way we do it is by identifying expectations of a spin operator. So the operator satisfies the usual commutation relations for spin. And then what we'll do is in the classical limit, these expectation values of the operator will be identified with the classical ring radius. And the usual law, I guess, is that a classical, like a multiple of order S requires scattering two S, like states of, I did it in the reverse as well. If you want the S multiple, you should be scattering S over 2 states. Okay, but I would argue that the way we approach it is not quite like that. We don't take a fixed spin limit. So if you take a spin 5/2 amplitude, we don't tend to take a classical limit of a finite spin. For us, a classical limit involves some sort of infinite, like you have to be able to trace the behavior of spin as it goes towards, like goes to infinity. And what's the reason for that? Well, if you want to say compute the variance of your operators, that only vanishes when spin goes to infinity, either in a coherent state approach or in like a large spin approach. So maybe like this is the better photo to have, image to have. So,
But then does that mean those are not linear?
Maybe we should.
Yes.
Finish.
so maybe this, yes, exactly. So it depends what you want from your theory. It's just to say at 3 points, you can write any 3-point amplitude in terms like in this basis where you have this structure of your spin multiple and some coefficient. And in general, for a generic amplitude, this coefficient depends on the spin of the state that you're scattering, right? I mean, if you like, there should, in principle, you'd think generically, you should know if there's a difference between scattering spin 2 or spin 1. This is not, at no point have I done anything classical here. I've just rewritten things in new variables. Now, if you do this on the 3-point amplitudes of Kerr that were written, you find by chance that they have that they are universal, that they don't have that spin dependence. If you choose a different set of 3-point amplitudes, like the leading register states, you find that they're not universal, they have some complicated spin dependence. And only when you take this spin to infinity, so you take the limit of this coefficient here, do you recover the expected classical linearized energy momentum tensor. Now you can ask, should I interpret the spin universality of the 3-point amplitude as a property of the Kerr QFT or as a chance that happened at 3 point? And that's up to you a little bit, right? You can decide if that's your feature. I would say it's extremely hard to get true spin universality to work because you have correct, when you change, it's a bit technical, but when you change your representation of your spin operator, you will pick up correction terms, which are not like even at the 4-point, like nice amplitudes, you pick up correction terms, which only in S to infinity vanish, and then you get this exponential. But if you don't take S to infinity, you don't get this usual exponential, which we associate with the 4-point Kerr amplitudes, which contain the spurious pole. Very technical, I'm sorry. We can talk about it after maybe. But so this is definitely something we noticed. Okay, so the benefit is that either approach, so either taking a large scattering of a large spin state or some coherent state, which ultimately also depends on some infinite behavior of your amplitudes for infinite spin, you get the same classical amplitude, right? So they're just two ways of looking at the problem, and you can choose whichever one you prefer. And in particular, this one's really nice with the polynomials, because our polynomials essentially resum and become exponentials. So the amplitude I wrote previously now can be written like this. It's like the classical contributions. And now we have these 4 different spin-dependent contributions. We have 2 entire functions. They don't look entire, but they are. This is just, I guess, the feature of how to write them. But if you just expand them, they're perfectly fine. There are no poles. And now you can ask, okay, what other features does this amplitude have? It matches the expected multiples up to spin let's say up to the dipole it matches. It's even in Z, which is a mod A term, which means that you don't have mod A, right? It's all A squared. And what we're going to do now is construct these coefficients, or I'm going to flash what we do. We construct these contact terms out of the polynomials in the QFT, and then essentially use the classical limit procedure to bring them back. to classical
Sorry,
limits.
just one question.
0 minutes left. Yes.
No, later, afterwards, offline, yes.
Okay. 0 minutes, so I'll say it really fast. So what we do is we match to some data that we have up to 8 to the 4. And that just actually comes up to like adding one quantum contact term, which is a function of the polynomial, which is able, which then actually generates infinite amount of multiple corrections. And then what we're going to do is compare to black hole perturbation theory results. So really, what is it like? Let's compare to the case when you scatter gravitons off or a plane wave off a Kerr black hole background. So as I said, we match and fine, this is the quantum contact term, but when you take the classical limit, it looks like this, again, entire function. And what does it do? Well, if you compare to the results by, I guess, what's this in the audience and Vines and co, it essentially means that our amplitude plus this contact term is like reproducing all the terms available that have been calculated. So that's 8 to the 6 explicitly in the literature. It computes them perfectly. And all we need to do to get like some non-conservative terms is add one contact term. And then the parts that we're less certain about are these terms proportional to alpha. And okay, you can ask what's alpha tagging? In the original paper, it was related to some polygamma contributions from solving the Tarkovsky equation. But there's definitely more to understand here, and to understand why alpha equals 0 is such a nice solution, which we are able to reproduce in terms of exact functions, whereas the terms proportional to alpha seem to be not exhibiting a lot of structure. Okay, right, this we see is this, all these terms are generated by the first contact term, all these are generated by the second contact term. And I'll leave it at that. Thank you.